sustainability webinar from the Duarishka project. And specifically today's one is on the theme of hydropower, the opportunity, design, and some results from our pilot projects. My name is Angus McNabola. I'm a professor in energy and the environment at Trinity College Dublin in Ireland, and I'm the leader of the Duarishka project. So I'll be chairing this morning's session, and which will be mostly delivered by my colleague Daniele Navarro, who I'll introduce in a second. So before we kick off, I just want to spend a couple of minutes mentioning a few things, a little bit about our webinar series, about our project, and just an introduction to today's session, and also a few house rules. So all in all, today we're scheduled for an hour, but possibly will be about 40 minutes, depending on the number of questions that are involved. So first of all, to introduce the idea of the Duarishka project and what we are doing in general here. The Duarishka project started back in 2016 and has been generously funded by the Interreg Ireland Wales programme, and looks at water and energy or energy efficiency in water systems of various kinds, and has been working hard on coming up with various technologies and practices and policies to try and improve the energy efficiency of water use and also water supply. And an example of that is on the theme of today's webinar, is the use of hydropower turbines in water networks. So within the theme of the project, there are a couple of other aspects of technology that we're also working on, which would feature in some of the other webinars that maybe you might be interested in. These are shown in the little circles here of the various aspects of the Duarishka project. So aside from hydropower, we're also involved in recovery of heat from wastewater, the control of water networks to be energy efficient, the benchmarking of water utilities, the environmental impact of a variety of technology interventions or life cycle assessment, and so on. So that's the kind of a flavor of the project and where it comes from. In terms of the webinar series itself, starting today, our topic is again on low-cost modular hydro turbines, and I'll mention a bit more about that in 1 second as an introduction. But we'll also have a couple of other webinars happening later next month in March, and also one in April, on those other themes of the project to do with heat recovery and wastewater. So we have 2 of those, one on the opportunity to recover energy and one on doing it in practice, and also a webinar on benchmarking of water utilities in Ireland and Wales. So the topic of today's talk is on low-cost modular hydropower turbines. So where this originates is from many years of work within this Duarishka project, and also some preceding ones, which were also funded by the previous Interreg Ireland Wales programme, which looks to try and come up with technology that can, in an economically viable fashion, exploit some of the small hydropower opportunities that are available in water networks. So we've known that these exist for many years, but conventional turbines are generally quite expensive when we get to the scale of hydropower we're talking here, which is generally less than 20 kilowatts or something in that region. So I won't give away too much of the details of all of that. I'm going to leave that over to my colleague Daniele. But just before I get on to introducing Daniele, a few things about the webinar. So we're going to have a slide presentation from Daniele to follow shortly, followed by a discussion and some questions and answers from you. So if you have any questions either now or as you go through, please put them in the chat, and we'll try and get to them at the end. Also, it would be great, as we're I'm sure we're all used to webinars and remote meetings now, but if you feel you would like to, it would be nice to introduce yourself on the chat. Please do. Sometimes the names appear as your username and so on, and it's difficult to identify who you are or what organization you're with. So we would welcome you to say hello and who you are if you want. As the etiquette for the session, please keep your cameras and microphones off until the end when we're having the discussion. And also please note that the webinar, I'm sure you can see in Zoom, is being recorded, and we'll make this available for others who couldn't join today. So then without further ado, on to our speaker is one of the long-standing members of the Dual-Riske team, Daniele Novara, who has MSc degrees in engineering and management, and also has recently finished his PhD on the development of small-scale hydropower energy for, well, mostly focused on pipe systems, but any small-scale hydropower application. So I guess I'll hand over to Daniele, who is the real expert on the implementation of this, and I'll stop sharing for a minute, and Daniele, you can take over.
Perfect. Thanks, Angus, for the introduction. I bet you can all see my screen.
Yep.
Perfect. So in terms of what my short presentation covers is we're talking about just a few general points about renewable energy, especially on the small scale. Then we're gonna go through the technology that we've been developing and testing in the various projects with the Trinity College and the various partners. And then discussing also the practical application in the end, the lab tests and the practical application in the two Dual-Riske demo sites. So in terms of in general, so as we all see, there is a growing trend of the penetration of renewable energies in the market. There is a even more growing widespread application of those. And this is going down, especially to the small scales, not only on the utility scale. So we are talking a lot about an increase of distributed generations. And well, there are many technologies available, but most of the small scale, the micro scale installations nowadays are made with especially with solar PV or small wind turbines. And those two are type of devices that in the last decades or so have dramatically decreased in terms of investment cost, and have been modularized and just made available more or less off the shelf, even in a small scale, even down to domestic applications at a reasonable and ever decreasing cost. At the same time, hydropower is a very mature technology that has been around for over 150 years or so in the current form. And however, normally historically it has been applied to large power stations, and even nowadays almost the entirety of the hydropower turbines that are available for purchase from private and for companies are custom made. So they are designed, they have a specific engineering design to suit the conditions of a particular site. And therefore, so this factor of the high resulting investment cost due to this customized manufacturing approach has largely hampered the diffusion on the micro and small scale of hydropower in comparison to solar PV or wind turbines. And so therefore the technology that we've been focusing in for the last few years consists of a standardized hydropower type of device, which are pumps as turbines, which are basically just regular off-the-shelf centrifugal pumps used in reverse as a turbines. so with the attached motor working as generator. So the main advantage is the low purchase cost, which is just a fraction of that of a conventional custom-made hydropower turbine. They also are very compact in dimensions. They are mass manufactured product with short delivery time and very easy to do the maintenance of, and thanks to economies of scale, and also with spare parts available at a very short notice. And also these type of devices can work in a fully pressurized pipeline, and therefore allowing for back pressure downstream of them. Despite this, however, there were a number of challenges that we had to face. So, for instance, the lower the efficiency at partial loads with respect to custom turbines, which made the design and the selection of this type of devices very critical. And then a series of uncertainties, which basically are down to the fact that these are devices that are sold as pumps and not as turbines. So in most cases, their performances are not available from the manufacturer. And at the same time, we were facing an absence of proven or established design guidelines for installations with these pumps as turbines. And just to give an idea about the type of power range we are talking about, we are mostly focused on the less than 100 kilowatt scale, which is enough to power a dozen or so households. However, these type of devices can also be applied on the household or in the pico generation scale with less than 5 kilowatt. You will see that the two pilot sites that we've built with the Du-Rischke project fall under this category. However, it's kind of an extreme boundary. And at the same time, these are devices that can also be applied for larger powers, even larger than 100 kilowatt. However, only on special applications, for instance, when the working conditions are pretty much fixed in terms of flow rate and pressure available. In terms of applications, there is a very wide range of applications for these type of devices, and there have been some sporadic examples of previous installations over the last decades. For instance, those are the devices that can be installed. These pumped turbines can be installed for more traditional run-of-river hydropower, where there is an intake on a water stream, and then an elevation difference that can allow the designer to install a penstock to create a pressurized column of water and then feed it into the turbine in the powerhouse. So which is a quite traditional, let's say, hydropower scheme, even though, of course, here we are talking about rather small type of power output. And this type of inexpensive and easy to maintain device, therefore, are particularly suitable for rural electrification in developing countries, where access to particular and more specific hydropower spare parts of custom turbines is more difficult, and so on. Then another application of these devices is the energy recovery from existing pressurized networks, where basically in every water network, whether it's a drinking water, it's a cooling water, it's a mine supply system, and so on, and there will be a number of control valves, here indicated, or pressure reducing valves, PRVs, and which basically create a differential in pressure between upstream and downstream. And this type of potential can be also exploited by installing a turbine in parallel to those valves, which basically, so instead of dissipating that potential by like heat and noise, you could recover part of it as electricity. And as I mentioned, there is a big variety of applications, basically whenever you have water moving around in pipes. Other uses of this technology are to upgrade hydropower, like hydropower or general hydraulic infrastructure, which is not currently being used for power generation, but also to integrate existing hydropower schemes, for instance, to generate some base load of power during the dry periods of the year where the main turbines have to be switched off. And however, so when we started looking at this technology, we started interacting with a lot of policy and industrial partners, and eventually found out that there were some barriers to the adoption of these devices. So we started our investigation by asking the questions why we don't have these type of pump-as turbines already implemented everywhere. And we basically boiled that down to three aspects. So from the point of view of the device manufacturers, so the pump industry, we didn't find a big interest at the time when we first contacted them on the use of pumps of their product as a turbines, essentially because it's a different market than the one they are traditionally used to, and they see that as marginal. Then on the side of the hydropower designers and consultants and practitioners, there were a series of highlighted concerns. We found first of all a general unawareness of the possibility to use this type of devices instead of a conventional turbine. Then a general lack of experience with them, and also the presence of feed-in tariffs that were granted to hydropower installation in most European countries until a few years ago. They were favoring very efficient turbines, since the remuneration was very attractive for the kilowatt hours generated. However, these type of feed-in tariffs have slowly been removed from most countries around Europe, and therefore we think that the current landscape makes things more interesting for a cheaper type of device, which doesn't reach this very high efficiency of a custom turbine, but it just costs a fraction of that. And finally, on the side of the potential users, so mostly industrial users, for instance, water utilities, we found a general risk aversion and again a lack of awareness about the possibility of generating power by means of these devices. So as a first thing, we tackled the problem of the selection of the most ideal pump-as turbine for a certain site. And I'm not going into the details, but just you can imagine that there are thousands and thousands of conventional, off-the-shelf available water pumps that you can buy from many suppliers. And probably a good number of those if installed at a particular site will output some power, but since as I mentioned, the efficiency at partial loads tends to decrease quite dramatically as you move away from the optimal working point. As a result, it's critical to select the one or two models that are most suitable, that can give the highest electricity yield, that can minimize the payback time and maximize the carbon savings over the lifetime of the installation. And therefore, so we set out to work on a design software that allows the selection of the optimal pump to be used as a turbine for a given site. And this, as you can see from the scheme, so this takes into account a variety of factors which are both technical and related to the fluid and hydraulic dynamics of the device, but also economical, environmental, and so on. And in the end, what this software does is that taking data from the catalogs of pump manufacturers, it enables a visual choice according to a variety of parameters. For instance, the electricity yield per how many kilowatt hour you can produce per year, or what's the payback time, and so on. It allows the designer to have a visual feedback of which one or which ones are the optimal pumps that can be chosen to work as a turbine for a given site. For instance, on the right-hand side, it's an example of a results tab in which all those the black dots with a certain uncertainty interval are all existing off-the-shelf available pumps, and therefore, for instance, in this case, when we are looking at what's going to be the yield of kilowatt hours that the device can produce per year for a specific site, the choice would go into the devices that are closer to the peak of the chart. So in order to validate these, in order to validate the results from the software and to get confident into the design of the following demo sites that I'm going to talk about soon, we first set out to build a hydraulic test bench for turbines and valves, which is located in the civil engineering facilities of Trinity College in Dublin, where we have tested a variety of different configuration of valves, turbines, generators, and so on. And all of this knowledge went then into the design of the two pilot plants, the two demo sites. So the first of them, located in Wales, has the look of traditional, in a way, hydropower, in which we have a natural body of water, a small stream, from where we've built an intake, which diverts a portion of that water into a buried pipeline, and then 300 meters away from there into the turbine, hosted by a small powerhouse, and then back into the original river. The setting, however, and the type of power is very innovative, because this project was developed in collaboration with National Trust, who is the landowner, and the purpose of it was to give power to the historical farmhouse that you can see in the left-hand picture, which hosts a big collection of Bibles from ancient times, and therefore most of the electricity produced is used as self-consumption to run the lighting and the heating and the humidifiers systems to preserve the rare Bibles collection. And in terms of power output, so we were below 5 kilowatt, so which is more or less a household type of generation plant, and the timing was very fortunate, because when we got in touch with National Trust, they were already, well, here you can see, by the way, the internal side of the powerhouse with the turbine and the electrical devices. But as I mentioned, so when we got in touch with National Trust, they were already planning to develop this hydropower installation at the site, and what the options that they were considering before getting in touch with our team were either a set of 3 Pico turbines, that are a type of standardized turbines that can output just over 1 kilowatt, or as an alternative, a conventional Pelton turbines, which is one of the classic type of devices for this type of for hydropower in general. And And then at that point we stepped in and we suggested instead a third way, which is using a pumped turbine type of device. Then and then in the end, the configuration chosen was the one with this G83 connection standard, which was then later upgraded to a different one. But that was you can see that in terms of cost in pounds, there was a big difference going between, especially between the use of pumped turbines and the custom-made, the regular Pelton. And this cost difference in the devices then resulting in a big, very large savings on the final price tag of the installation, which was just below 30,000 euros. But most of it actually went into civil works and planning and commissioning, while only just 15% of the number was made up of the turbines, electrical devices, valves, and various bits of equipment. However, if instead of 3,300 pounds pumped turbines, they had decided to go for a regular Pelton turbine, then the final price tag of the whole installation would have been almost doubled. And I'm just going to show regarding the Irish pilot plant. I'm just going to show a few seconds of video.
What we're trying to do in the Dúrishka project is use the pump as turbine, which you can see over my shoulder here, to reduce pressure in the system. So it also does the same thing as these valves, reduces pressure, but it produces electricity as a byproduct of that. So in this technology, it has a kind of a double benefit. It reduces pressure, reduces the amount of water wasted through leakage reduction, and also generates electricity. And this system is what we have put in place in the Blackstairs demonstration site, and it reduces the energy consumption there by up to a quarter.
And we were excited to hear about this new technology that can harness the energy from the water. And our committee, which runs the scheme, were eager to find out more and to see would our scheme be suitable for this project. So with some exchange of data and more meetings, etc., eventually in 2017 we had a feasibility study done by the Dúrishka team. And while the feasibility study identified a number of places throughout the scheme that would have the potential to create energy, by far the best place was up at the treatment plant, where there was the great head of pressure and also the volume of flow, which was enough to generate 4.2 kilowatts of electricity. So right beside it then there was the treatment plant, which had the use for this electricity. So it's very important to have the conditions to create the energy, but you need a use for the energy nearby. So it was an ideal location.
Okay, so as you've seen from the introduction, so for the Irish pilot plant, we've decided after an initial selection phase to collaborate with the Blackstairs Group Water Scheme and with EPS that was operating their treatment works to install a turbine at the raw water inlet from one of their gravity-fed lines. The final, so the regular the steady-state power output that we envisaged ended up to be just about 3 kilowatt, which doesn't sound like much, but covers between 20 and 25% of the energy demand of the water treatment plant on site. And as you've seen from the drone overview from the video, so the scheme has a river source, then conveys water into a settling tanks. Then there's about a 2 kilometers buried pipeline, and previously water was just splashing on top of the storage tank, as you can see on the bottom left. So that is the water power that we have instead recovered by installing a turbine on the terminal part of the pipeline. So instead of just dissipating it by having the jet splashing inside the tank, we designed this system, which in very basic terms just allows water, diverts water into the turbine before ending up in the same tank. And this is just a few snapshots of the construction. So in terms of installation, it was quite straightforward. It just needed some excavation to expose the supply pipe, the installation of a vertical T, as you can see on the bottom, and then just the making of a small turbine support concrete pad. And finally, all the plumbing could be completed. And this is the final layout as you saw from the short video clip. Here, so we can you can see that, well, first of all, the cost was just below 30,000 euros. However, this included a number of monitoring equipment, for instance, that is not necessary then for a commercial installation, and therefore we envisaged that the price for a similar type of scheme to be about half on a commercial setting. And as you can see, the power generation per month has been quite substantial, and from the startup of the scheme in the middle of October 2019 up to the beginning of summer 2020. Then, of course, as expected, the monthly power has gone down due to the dry season. However, in the first balance from the 12 months, initial 12 months of operations was very positive, and over 2,000 euros were saved on the electricity that was, so all the import of electricity that was avoided by the treatment works, corresponding to 4.5 tons of CO2 saved. And in the meantime, connected to other projects and other settings, but the team that assembled in Trinity College that I'm part of, as Angus and the other colleagues, have been working also on other side projects. So for instance, on a 3 kilowatt energy recovery turbine in a Spanish irrigation network, and on a 30 kilowatt turbine in an Irish, in the water supply of an Irish underground zinc mine. So we started seeing more and more of this, of opportunities for feasibility studies and for this type of actual installation of these devices. So as a conclusion, with respect to the initial challenges that we were facing a few years ago, when we first identified when we took a snapshot of the current landscape of the technology and of the willingness of different parts to innovate. Respect to that time, nowadays we've in the course of the Durischke project, we've talked with a lot of pump manufacturers, and we've observed a change in their attitude. So some of them they have a much more proactive interest in the use of their devices as pumped turbines now rather than 4 or 5 years ago. And at the same time, so by rolling out the design software, by showing that the applicability of the design of the design and the use of pumped turbines in different settings, and also of course the 2 pilot plants were instrumental to this, and by all the networking and that when it was around, especially the Durischke project, we talk and we discuss, and we've been disseminating to a lot of hydropower designers, practitioners, and so on, the use and the advantages of this type of technologies. And at the same time, we also with all these dissemination activities, of which this webinar, the present webinar, is a part of, we have also worked a lot to inform the potential users, for instance, water utilities, landowners, and infrastructure, various hydraulic infrastructure owners, and so on, about the potential of this technology towards their decarbonization efforts. So that's all for my presentation. Thank you very much to everyone attending for your interest and for your time. If I would just like to mention that we are still offering as Durischke project feasibility studies and support and guidance if you are interested in evaluating the applicability of a pumped turbine or other type of hydraulic or energy recovery devices in a setting you know. So feel free to reach out by email or to me or to other people in the team. So thank you very much. I leave it to Angus.
Yeah, thank you very much, Daniele. Thanks for that presentation. That was very good, if I do say so myself. So now we've passed into the question and answer. So again, welcome questions from the audience. You're welcome to either put them in the chat, or if you want to ask it via your microphone, you can raise your hand using the raise your hand function. So while you're busy working on those questions, I just want to remind you about our other webinars that are again occurring. The next one on the 10th of March on heat recovery from drain water or wastewater. So I'm going to be looking into the background of that and the feasibilities and opportunities for implementing it in Ireland and Wales. And then there are a follow-up one later in March on a couple of examples of doing that in practice, similar to this with some demonstration plants. And finally, in April, we have a webinar on benchmarking of water utilities. I think we also have some, if you want to get in touch with us afterwards, we have a contact us section here, so via our website or via the email address that Daniele put up. And we have a number of YouTube videos, such as the entirety of the video that you saw a little clip of earlier is on our YouTube channel, and all of which you can access by joining our Smart Specialization Cluster, which is another way of saying our little network on water and energy. So that's it as a summary. In terms of questions from the chat, I'd also appreciate if I just put in the chat when we do wrap up. We have a little feedback form, which we'd appreciate if you have the time to just fill in. It is very short, so that we can see what you liked and didn't like, and then how we can improve things. But anyway, over to the questions. So first of all, I have a question from Jan. Thanks for the question, Jan. It'd also be great if questions, we could have an affiliation as well, so we know where you're from. So anyways, Jan's question, what would have been the electricity production if the Pelton turbine was chosen in, I guess that's in the case of Timau or Wubernant in Wales?
Yes, thanks, Jan, for the question. Actually, the electricity production, the capacity would have been the same, because we were constrained to stay under the 3.68 kilowatt that, according to the UK regulation for grid connection of renewables, is the limit below which there is a simplified essentially there's a simplified procedure. So even though that stream allowed and the water abstraction permit allowed up to 20 kilowatt of turbine to be installed, in agreement with National Trust, it was decided to stay below the 3.7 kilowatt because of that. Otherwise, going for a different type of more expensive grid connection standard would have increased a lot the construction and permission costs.
Yeah, great. It's also worth, on a related note, even though the stream has potential for 20 kilowatts, we don't necessarily have that demand for energy at that location, which is a very rural location. So the size of the installation we put in fits well the need of energy that was there. And also, if we went up to 20 kilowatts, if we did have that need, of course, we could still have used a pump-as turbine for that. And I guess we also had a similar situation in the Blackstairs scheme, in that we ended up with a 3 kilowatt turbine, which was limited by the size of the pipe that was supplying the treatment work. So let's say if that plant was being designed from scratch, and it went with a slightly larger pipeline, which had less head losses in it, we could have ended up with a much larger turbine there, and saving more of the energy required for the treatment works, probably 50% versus what we get now, 25. So great. On to the next question. We have one from Grenner Ham. So I'll just read that as a long description. So here's the question, Danny. I'd be keen to know about the efficiency of the turbine set in Wales. Why a turbo turbine wasn't considered, for example. Seeing as we're looking at the total project cost difference of approx 5%, the only difference being the cost. I'd like to know the difference in electrical efficiency and see whether there's a long-term financial benefit.
Yeah. So the initial market, the initial market analysis of looking at different type of devices was done by National Trust. So in terms of but I mean, yes, from a technical point of view, a turbo turbine could surely have worked. We have just about 34 meters of head of gross head available at the site. However, so in terms of efficiency, the pump-as turbine over there is over. So the overall efficiency is about 70%, which is definitely comparable to the peak efficiency that a bespoke turbine can have at that type of site. So to counteract to mitigate the effect of having of a low partial load efficiency of a pump-as turbine, we've decided to go for a variable speed operation type of routine. So so this basically allows up to some point to counteract and to mitigate that initial drawback. So in the end, if the so in terms of payback time, with the alternatives that we had, having a pump-less turbine allowed us to stay below 10 years, with less than 10 years of payback time. However, with the other turbine options that we had, we would have been way much like 14, 15, 16. So this is what, this is for the consideration and for the design that the way that we worked.
Great, thanks, Daniele. There's a couple of more questions in. There's a comment from Paula Tracy that Waterways Ireland is interested in possibly benefiting it, and then there's a question that follows that up. So can you comment on the nominal head required for these devices and the implications of parcel load? How often does the PAT have to be run to be worthwhile? And flow rate. So I guess we're asking for what are the kind of minimum heads and flow rates, and how do we deal with the partial load limitation?
Yes. Well, yeah. So first of all, about the I see from Claire about an inquiry about the noise of the device. It's absolutely comparable to that of a Pelton or another type of turbine. It's so when it's running and connected to the grid, it's pretty silent. On top of my head, I think the one at both those two devices at the two pilot sites are about 65 decibel of noise at 1 meter. So they don't disturb a conversation if you stand by it. In terms of of nominal head and flow, so essentially the boundaries, the minimum head is around 7-8 meters, depending on the flow available. And in terms of the minimal flow, we are around a few liters per second, let's say. So from 10-15 cubic meters per hour on. In the end, the power that can be produced by any hydropower device is the product, is basically a product of some coefficient times your flow and your head. So the more you have of both of them, then the more power you can recover. And there aren't really upper boundaries, at least not for this type of power outputs of under 100 kilowatt, because you can find pump-less turbines that will work up to hundreds of meters of head and of cubic meters, a few cubic meters per second of flow. And in terms of implication of partial loads, it's much of a case-by-case type of rule. There is no fixed rule in the sense that the more the flow and heads are constant and during the year, the better it is. But there can be different settings in which even an intermittent flow and head pattern can be fit to suit a pump-less turbine. It really depends on the case.
Yeah, a good example of that, there was one picture of in Daniele's presentation, was from a related project to the Dual-Ishki, which is Redon, which is funded by a different branch of Interreg, but that was in an irrigation network, in which the flow is very variable, so it was installed on a pipeline supplying water to a variety of crops, but mostly walnuts, and so that was intensely irrigated during the summer, but had no flow at all during this time of year, for obvious reasons. Yet in that situation it works, and it really comes down to trying to control the flow rate to be close as possible to the fixed working point, coupled with the fact that the turbine costs you know, in the region of 1/10 of what a conventional turbine is. So because the cost is so much lower, that disadvantage of its poorer part load can be overwritten. But as Daniel says, it's case by case. It's not that every scenario it'll work. So and on that, we're happy to look into any of these cases for you for the next couple of years. We essentially need flow and head information, and we can provide that answer. So I guess there don't appear to be any more questions in the comment section. So I guess we can wrap it up at this point. I just want to thank everybody who took the time to listen to us. Thank Daniele for his great presentation and work on this. And again, if you haven't had time to fill out the feedback form, just remind you that it's there in the comments. It would only take a minute or so. So thank you all for this. It was mentioned at the start and asked in the comments, was this recorded? It is being recorded, and it'll appear on our website there, dual-EU, in the very near future. So thank you all, and I hope that you can attend one of our next webinars on the 10th of March. Okay, so thank you very much.